Thank you for coming to my presentation. I am Machi Shinmei. I'm from North Carolina State University. Today I will talk about learning a policy primes quality control towards evidence-based automation of learning engineering. One of the problems in MOOCs is that creating effective large-scale online courses is very hard. It requires lots of efforts to create effective instructional components such as videos and reading text and quizzes. Even though there are some existing design theories for building courses, they still require labor-intensive iterative engineering. Therefore, there is a heavy demand for practical methods to efficiently create effective online courses. Especially, one of the challenges is to identify issues with the courseware. There are some common analytic techniques, such as learning curve analysis and item lesson theories. However, these techniques can be only applied to assessment items. On the other hand, online courses consist of various types of components, and these type of components should be subject for improvement. As a solution for this problem, we propose RAFINE. RAFINE stands for Reinforcement Learning Application for Incremental Courseware Engineering. RAFINE is given a student's learning data, and it automatically identifies relatively less effective components on the existing courseware. We propose RAFINE as the building block for the evidence-based, human-in-the-loop, iterative learning engineering method that we call RAFINE method. This is how RAFINE method enables the human-in-the-loop iterative learning engineering. First, students use online courseware, and we collect learning trajectory data. All student learning trajectory data will be consolidated into a single Markov decision process. Here, the state represents the student's intermediate learning status, and action represents the instructional components that student took at the state. Given the Markov decision process, RAFINE apply reinforcement learning technique to compute the converse policy. Converse policy is different from the normal policy used in reinforcement learning. Converse policy suggests the least optimal action at each state. After that, the converse policy will be holistically interpreted to find the components that have least contribution to students' learning. The list of detected components will be provided to courseware developers as a recommendation for refinement. Courseware developers will modify the courseware based on the recommendation given. This is how RAFINE method works. I will talk about the converse policy and holistic interpretation next. Reinforcement learning is generally explained like that. Given a state transition graph, or Markov's decision process, with goals and delivered for each state, it computes a policy which shows optimal action to be taken at a particular state. In RAFINE, learning trajectory graph is given as a state transition graph. Suppose this is the learning trajectory path that one student went through during learning on the courseware. Here, the state represents the student's intermediate learning status, and action represents the instruction components taken. Final state represents the final letter grade. Learning trajectory graph is a consolidated graph of all student learning trajectory paths. So, it looked like this. Given a learning trajectory graph, RAFINE computes the converse policy. Converse policy suggests an action that has the least potential to reach the ideal learning goals. In the graph, the orange arrows shows the converse policy action at each state. As it's shown, the converse policy shows the path the students do not want to follow. Although converse policy tells the least optimal action at each state, this type of prediction doesn't help us with achieving RAFINE's goal. This is because we do not care about which instruction component has the least contribution to students' learning at each state, but we are interested in the usefulness of the components across all over the state in the learning trajectory graph. So we holistically analyze the converse policy. We call this interpretation holistic interpretation. For example, look at video 1. It appears lots of times in the Commerce policy. That means Video 1 is ineffective in many situations, and that suggests Video 1 is a good candidate for improvement. Holistic interpretation of a policy, analyzing a collection of actions suggested as a policy over all states, which we call policy action set. It tells the usefulness of the actions. This is different from the way that the traditional application of reinforcement learning uses the policy, which we call atomic interpretation. Atomic interpretation tells which action should be taken at each state. On the other hand, holistic interpretation tells the usefulness of individual action by interpreting the Commerce policy as a whole. So, about the holistic interpretation, we have this hypothesis. That is, by holistically analyzing a policy action set, relatively ineffective actions can be identified. In the current applications, that means by holistically interpreting a policy action set of a Commerce policy, we can evaluate the effectiveness of instructional components. So, how can we interpret the Commerce policy holistically? We propose frequency heuristic to do that. The hypothesis under frequency heuristic is this. Relatively ineffective instruction components tend to appear in a policy action set more frequently than effective ones. So, in the Lafine, we use frequency heuristic, and instructional components that frequently appear more than the predefined cutoff in a policy action set are included in the recommendation for refinement. Then question is, how frequent is frequent? We evaluated two different cutoffs. One is mean frequency plus standard deviation of the frequency, and the other is mean frequency minus standard deviation of the frequency. Let me explain the frequency heuristic with examples. This graph represents the frequency of each instruction component in the policy action set. Remember the learning trajectory graph I showed before. The orange edges represents the instruction component suggested as a Commerce policy action. Here, we count the number of times that each instruction component appear on this orange path. Once we calculate the frequency of each instruction component, we can calculate the mean and the standard deviation of the frequency. When we use mean minus standard deviation as a cutoff for the frequency heuristic, the instruction component whose frequency is above the n-60 cutoff will be classified as ineffective components and be included in the recommendation for refinement. If we use mean plus standard deviation as a cutoff for the frequency heuristic, only two instruction components will be classified as ineffective and will be included in the recommendation. This is how frequency heuristic works. In this study, we have these research questions. First, can a Commerce policy correctly differentiate ineffective components from effective ones? And second, how robust is the Commerce policy against the different conditions of the learning data? And the third, how accurately does the frequency heuristic compose a recommendation? To answer these research questions and provide a proof of concept Lafine method, we conducted an evaluation study using the simulation data. To apply Lafine, each instruction component is required to be tagged with the skill. However, as far as we are aware, no such online courseware is currently available. So, we provide the proof of concept using a hypothetical student's learning trajectory data on mock online courseware. And this result will justify future efforts. The mock online courseware we generated consists of videos, quizzes, and hints, the total of 18 or 27. Each component was coded either effective or ineffective. So the refine's goal is to find ineffective components and include them in the recommendation. Mastery level of students also simulated using a logistic regression model. Here, effective instruction components increases mastery level more than effective ones. This is the difference between effective and ineffective components. To investigate the robustness of the Commerce policy, as stated in the research question 2, we prepared different kind of learning scenarios. First, we created 3 different courseware quality. We controlled it by changing the ratio of the effective components on the courseware. Second is contrast. Contrast was controlled by changing the difference in impact of instruction components on mastery level between effective and ineffective. The larger the contrast is, the larger the difference of the impact on the mastery level. So in total, we have 9 different learning scenarios. For each scenario, 100 instances of courseware offerings were simulated, each with 1,000 students. That means one learning trajectory graph consists of 1,000 students' data. Here is the result. First, we compare the frequency of each instruction component in policy action set. The purpose of it to investigate if the Commerce policy correctly differentiates ineffective components from effective ones. Here, we used normalized frequency instead of using frequency directly. The frequency of instruction components in the policy action set were normalized using the number of appearances in the learning trajectory graph. This graph shows the mean normalized frequency of effective components and effective ones for each learning scenario. This graph suggests that ineffective instruction components are selected as Commerce policy action significantly more than effective components, and this supports the frequency heuristic hypothesis. Next result is about the recommendation. In this evaluation, we calculated the precision and recall score of the recommendation computed from each Commerce policy and took average of them. The blue solid line shows the precision and recall score when we use mean minus standard deviation as a cutoff for the frequency heuristic. The red dotted line represents the recall and precision score when we use mean plus standard deviation as a cutoff. This graph shows when the quality of courseware is low to medium, we should use M-SD cutoffs, the blue one. But when the courseware quality is high, we should use M plus standard deviation cutoffs, the red one. So in other words, depending on the quality of the courseware, we should use the different type of cutoffs. To answer the research questions, the comparison between normalized frequency suggests that the Commerce policy is robust enough to discriminate the effectiveness of the components regardless of the quality of the online courseware and the contrast. And the result about the recommendation suggests that over 90% of ineffective instruction components were correctly taken into a recommendation when an appropriate cutoff was used based on the maturity of the courseware. One of the limitations of this study is that there are several assumptions about learning trajectory data. One is that we assume that presence of the KC model, and second is that we assume students' mastery level is measured correctly. The variation of learning trajectory graph is very critical. Suppose there is only one path in the learning trajectory graph. In that case, the Commerce policy has no choice but to select the components appeared on the path as the Commerce policy action. One question that is not addressed in the current study is that how much students' individual differences affects the accuracy of the identified effectiveness of each instruction component. For this moment, we assume that the majority vote applies, that the big data overrides the human factors and detects latent trend. As conclusions, the evaluation study showed that the proof of the concept of Laffine method. We found that the holistic interpretation over the Commerce policy is potentially a powerful analytic tool for the quality control. More specifically, the Commerce policy induced by reinforcement learning can be holistically interpreted to provide an insight into the usefulness of instruction components on online courseware. As a future studies, it is very critical to evaluate the Laffine method in authentic learning settings. Thank you for listening.